Okay. So last time I discussed the heterotic string heterotic string theory, and but I needed to emphasize one important point, which is the number of supersymmetry. So we start with type 2 A and 2B string. So this is the superstring, closed superstring. Formulated as NSR for the left mover and NSR for the right mover. And we had the GSO projection for both left mover and right mover. And it gave rise to graviton. And then pair of gravitino with either same or opposite chirality. And then other field in the massless sector. So in particular, it gave rise to two gravitino, and suggests that you have n equal 2 supersymmetry. And indeed, in this formalism, you can construct supersymmetry charges, space-time supersymmetry charges for both left mover and right mover. And so you have n equal 2 supersymmetry. On the other hand, in heterotic string, we have only one supersymmetry because you have NSR sector for the right mover, but you have bosonic string. And so you have n equal 1 supersymmetry. Now the terminology of n equal 1 or n equal 2 is a bit confusing if you start comparing the number of supersymmetries and the algebra in different dimensions. Because typically we call the maximally allowed number of supersymmetry in each given dimension as n equal 1. But sometimes we use another terminology of n equal 1/2 supersymmetry, etc. So this is a bit confusing. So I think it's better to count the number of real supercharges or Hermitian supercharges. And so if you count the number of Hermitian supercharges, this has 16 supercharges. Whereas this has 32 supercharges. Okay, so this would be the proper way to count the number of supersymmetry. In contrast, the minimum number of supersymmetry that is allowed in 4 space-time dimension is 4. So in 4 dimension, you can have a spinor can be either Majorana or Y, and Dirac spinor has 4 complex components. If you impose Majorana condition, you have 4 real components or 4 Hermitian components. So that's the smallest amount of supersymmetry, smallest number of supercharges you can have. So there are 4 times there and 8 times there. So if you say, so I have not started discuss compactification, but if you compact by 10-dimensional string theory, either type 2 or heterotic, in a way that preserves all the supersymmetry, then you'll get n equal 8 supersymmetry in 4 dimension, or n equal 4 supersymmetry in 4 dimension. And that's way too many to be to have any relation to the world we live in. For one thing, the standard model particle physics has the feature which breaks parity. And in order for in particular, the weak interaction to break parity, it is important that the sum of the fields in standard model particle physics have chirality properties. That if you project the spinor field in standard model, depending on whether it has left chirality or right chirality, they interact differently and they have different kind of mass structure because of the way that weak interaction matches with the way that the mass of neutrino and electron works out. So, and the quarks works out. So that, but in order for that to work, it's very important that the low energy theory of whatever the fundamental theory you have chirality properties. And if you have more than n equal 1 supersymmetry, such theory cannot be chiral. So we'll probably be discussing it in the next quarter. So in order to go from higher dimension to lower dimension, you need to do that in a way that removes some of the supersymmetry. Okay, so that will be one of the main things we'll be discussing in the next quarter if you continue to attend this course. And so let me sort of, so today there will be a presentation by one group. And I understand that they're going to talk about Narayan compactification. So I shouldn't steal their thunder. So I'm not going to talk much about it. If there is anything I should add after listening to their presentation, I would add. But I shouldn't say too much about it now.
No, we're going to talk about wild anomalies.
Oh, okay. So it's actually so that was different from the because I think on Wednesday there is somebody who are going to talk about Narayan compactification. So I shouldn't steal their thunder. But there are a couple of things I just want to mention in order to sort of have natural connection to what I'm going to say. So Narayan compactification is a generalization of heterotic string construction. So in the heterotic string, we consider a 10-dimensional superstring for the left mover and 26-dimension bosonic string for the right mover. And these are flat spaces. But one can consider generalizing this in such a way that left mover and right mover lives in different space, but each are not just flat space, but can be more interesting space. And in the case of Narayan compactification, he considers that to be some torus. So what he considered is that the left mover is 10-dimensional space, but D of them is some kind of torus. And similarly, right mover is 26 dimension, but D of them is some torus. And then he considers some general configuration of this torus in such a way that you can actually nicely parameterize the continuous family of solution to string theory in this family. So that leads to this Narayan compactification. So he considered the following question. So if you have torus, then it gives rise to the lattice of momentum and winding number. And if it is bosonic string, you have this lattice makes the space of signature DD. And the reason it is important, the DD is important, is that the difference between the right mover and the left mover has to be integer. So this property has to be satisfied. So this was something we discussed earlier. So in general, therefore, it's natural to think, oh, by the way, so I didn't write it correctly. So what one should have done is that this space should be common. So you have to add 16 to it. So if you want to do that, the most general configuration of string propagating in a torus of this type should have momentum p left and p right, where this lives in d dimension and this lives in d plus 16 dimension, and satisfying the condition that is required by modular invariance. So he asked this question, and so essentially this reduced to the question of classifying the lattice 2D plus 16 dimensional lattice lambda of signature d plus 16, which is even, which is similar to this condition, and self-dual, which is required by S-duality transformation. So even and self-duality is required by modular invariance. Okay. Now, in the case of signature DD, was known in the case of in the case when D equals 0 for signature 016, we already saw that there are two types of lattice which satisfies this condition. So one is E8 cross E8, and the other is SO32 lattice. So there are two discrete choices of lattices in this case. For D plus 16 with D greater than 0, D positive, so in general it's like that. In fact, there is a single continuous family. Of lattices, and it turned out to be a homogeneous space, because what one can show is that if you have two lattices, they are continuously connected by rotation in this space. So modulo discrete identification, the space is a coset space. Okay, and then there are some discrete family, discrete identification, like this. But this part means that the family of lattices which satisfies this even and self-dual property is Grassmannian. So this type of space is called Grassmannian, and these are space of some hypersurface in higher dimensions. So in this case, what you do is you consider 2D plus 16 dimensional space, and you consider D-dimensional subspace of it, and you consider all possible configuration of subspaces, and that are classified by this continuous family. And that is the same as the family of all possible self-dual even lattices in this dimension with this signature, okay, which classifies the all possible heterotic string solutions of this type. Okay, so this is sort of important aspect, and in particular, I wanted to mention this parameterization of modular space, because I think I'm going to end in 40 minutes or so, because there will be another presentation. But I wanted to mention this part because this, I hope, will show up towards the end of this my lecture today. Okay, but what I wanted, the main thing I wanted to talk today is not Narayan compactification, which I think somebody will talk about on Wednesday. But rather the fact that you actually need to reduce supersymmetry. So as I said, in 10 dimension minimum amount of supersymmetry you can have 16. and the closed string has 32 supersymmetry, but in terms of number of supercharges. And if you if you, for example, put these string theory on torus, say, for example, using this type of Narayan compactification, then you are not going to break any of these supersymmetries. So that means that if you, for example, choose D to be 6 and compactify 10 dimension to 4th class dimension times 6-dimensional torus, for example, the simplest one could think about. So this is a toroidal compactification. Then you have too many supersymmetries to be realistic. As I said, if you have more than n equal 1 supersymmetry which correspond to 4 real components, then you cannot have low energy effective theory which is higher, and which cannot possibly describe, for example, weak interaction. So when you want to go from 10 to 4, you need to do that in a way that reduces the number of supersymmetries. That would be a minimum requirement. And one of the simplest way of doing it is orbitals. So let me start discussing orbifold. And so orbifold is the simplest construction. You can start from the toroidal compactification that reduces supersymmetry. So I will start with some example. So the first example I consider is our familiar friend that you consider a target space to be circle, but then introduce some action on this torus to modify the geometry. So let me explain what this is. So when you have a circle, you have this coordinate x, which say takes value from 0 to 2 pi r. And then we have periodic identification of x to x plus 2 pi r. So you periodically identify x. So, but you can think of also this as some kind of gauge symmetry. So what you do is you consider x to be originally on the real axis, which is to say that you think of x to be originally taking value in R, but then you consider this transformation, which I may call T for translation. So I define T to be translation by 2 pi R. And then what I do is that suppose I divide this R by the action of TR. So you identify these 2 points. Then this is the same as circle of radius R. Right? So in that sense, you can think of actually compactification, the field X, the string theory living on this circle, as actually gauge theory, where a gauge group is this discrete group of identification of X by translation. Okay. So you can think of this as gauge symmetry. So going from here to here, you can think of this as another gauge symmetry, introducing another gauge symmetry, which is to say that now I consider Z2 action to be going x to minus x. Okay? And so what does it do? So we have a circle of radius r. So you have 0, and you have pi r. And if you go to pi r, come back to the point. Now x goes to minus x, what does it mean? Well, if you combine this with this action, this is also the same as 2 pi r minus x. So namely that this is a reflection along this line. So you identify, say, for example, this point with this point, and this point with this point, and this point with this point. Right? You have this kind of identification across here. So therefore, you can think of S1 over S1 over Z2 as actually line segment from going from 0 to pi r. So in orbifold in this case means that the target space is now a line segment rather than circle. Okay. And so if you have a field theory on this space, then you would have to impose boundary condition on the endpoint, right? As I'm going to show you in the case of string theory, the consistency, in particular the modular invariance, automatically tells you what kind of boundary condition you need to choose for string theory on these endpoints. So there is a unique construction. And there's actually a very nice way to figure out how you can consistently carry out the quantization of string theory in this case, which is to think about Z2, so it's going from S1 to S1 to Z2 as gauging of the Z2 symmetry. So as I mentioned, this theory here has a global symmetry. That so if you consider a string theory, Borshit theory, whose Lagrangian is like this. This Lagrangian is invariant under x goes to minus x. And the periodic identification, this space, is also symmetric under x goes to minus x. So everything is symmetric under x goes to minus x. So it's a global symmetry of this two-dimensional quantum field theory. So what I'm suggesting to do to go from here to here is gauge this Z2 symmetry. And you can always do that as far as the symmetry is not anomalous. So gauging means two procedures. So in a modern way of talking about gauge symmetry, gauging means that restrict the Hilbert space, gauging G symmetry. Suppose the original theory has global G symmetry where G is some group. Then gauging means that restricting the Hilbert space to be G invariant. And then introduce G twisted sector. So if you do both of them, you are gauging this symmetry. Okay, so let me explain what I mean by that. So let's start from the restricting the Hilbert space to be G invariant theory. So in the original theory, the Hilbert space carries momentum, and then you have a harmonic oscillator acting on the state with some momentum p. Okay, and momentum p is given by n over r plus mr, so left mover, and the right mover has n over r minus mr. So momentum has left mover momentum and the right mover momentum. Okay, so therefore the partition function of the theory on S1 is q to the minus. So let me see. So it's a trace of q to the L0 minus 1 over 24 q bar of L0 bar minus 1 over 24. And this is equal to q over 1 over 24, and then a product of n, 1 minus q to the n goes from 1 to infinity, squared, and then you have sum of momentum and winding number. Okay, so this was the original partition function. This is a Dedekind eta function. Now, so let's first discuss a procedure restricting Hilbert space to be G invariant, which means that we need to do G invariant projection. So I introduce a projection operator which enforces the G invariance, where this action of G, so G is a non-trivial element of Z2, which flips X goes to minus X. Okay? So restricting Hilbert space to be G invariant just means that you insert this projection operator into the place. Okay? So you have 1/2 plus I plus G. So we need to do this calculation. So let me do that. We try to transcribe over here. So let's calculate T of Q of L0 minus C over 24, Q bar of L0 bar 1 over 24. Okay, so this is equal to 1/2. And because there is 1/2, so the P is equal to 1/2 of G plus 1 plus G. So the first term is the same as this, except that there is 1/2 multiplied to it. So you have product of P left, P right. Well, sum of P left and P right. Q of 1/2 of P left square, Q bar of 1/2 P right square, divided by n equal 1 to infinity of Q of 24, 1 minus, excuse me. Minus Q to the n absolute value square. So this is a contribution from this 1/2. Now, what happened? What about the contribution of G? Where G flips X to go minus X. So what in particular? First of all, what this means is that if the state has non-zero momentum, if the state has non-zero momentum, you have a state like that, and then you have non-zero momentum. If you act G on it, it flips every one of these. So it gives you -1 to the n, the sign. And moreover, it flips the momentum. Since the momentum is flipped, so it will not have inner product with the original state unless both P left and P right are equal to 0. So in this summation, if you insert G, all the non-zero momentums are removed. So you just have 1. And moreover, the sign minus is flipped because for each oscillator you get the minus sign. So therefore you get 1 over 24, or product of n equal 1 to infinity, 1 plus Q to the n, absolute value squared. So this will be the answer. This will be the answer for insertion of projection operator. So let's see whether this answer makes sense. So what the Hilbert space look like? Well, this space has non-zero momentum, and this space has no momentum, and counting of number of oscillators are exchanged. So for non-zero momentum, for zero momentum, both of them contribute with 1, and then the vacuum contribute with 1 because there is a 1 and 1, but there is 1/2. So this makes sense. Now, if you have oscillator, each oscillator here comes with 1 plus Qn plus Q2n, etc. And here you get 1 minus Qn plus Q2n, etc. And so if you have odd number of oscillators, they cancel. If you have even number of oscillators, they add up, but then you divide by factor 1/2, so each of them are counted by 1. So this is a correct counting. If you go to the zero mode part, if you go to the non-zero momentum sector, then this will not contribute. And this contributes, but with factor 1/2. Well, what does it mean that each momentum state is counted by 1/2? That does not seem to make sense because each state has to be counted by positive integer value. What happens is that P left, if you have P left and P right state, these are identified by this orbifold action by minus P right, P left, and minus P right, because it flips the momentum. It flips the coordinate, and that means it flips the momentum winding number. So these two states have to be counted by 1. What it means is that, for example, if you have momentum state, you have wave function like that. But this wave function is not invariant under Z2 action, because under Z2 action, it flips to minus Px. So therefore, the correct wave function that respect the Z2 invariance is actually cosine. So this is the correct wave function. So therefore, for each pair, there is one wave function that is Z2 invariant. So that's why we have 1/2 multiplied to it. So this is the correct counting. So it seems to me that if you just want to preserve the respect to the Z2 invariance when you gauge the Z2 symmetry, this is all you need to do. So this seems to be the correct partial function. However, this is not modular invariant. You can easily see that why this is not modular invariant in the following sense. That if you consider a partial function as calculating amplitude on torus, where in this direction you are going tau, and in this direction you are going to 2 pi, okay? And here you have 2 pi tau. Then this amplitude corresponds to just calculating this torus partial function in the original sigma model with the target space circle, and just multiply 1/2. And this one corresponds to adding the same thing, except that you insert operator which implement the G symmetry. That is that when you, what you mean, I mean, is that originally the original theory, S1 theory, has a Z2 symmetry. So that means that there is a delta charge. And by the Wigner theorem, we see that whenever a quantum theory has some global symmetry, then there must be unitary operators that implement the symmetry. So there must be some unitary operator that acts on the Hilbert space that implements the Z2 symmetry. So what we are doing here is just inserting this unitary operator which implements this Z2 symmetry, so that all the state that goes around this torus get this Z2 action. And that is what this is counting. Okay, but if you make this presentation, it is clear that just summing these two cannot have partial function, which is modular invariant. Because modular invariance amount to, modular invariance amounts to a summing over all the symmetry that exchanges the cycle. So if you draw a torus, like this, then the first two terms would correspond to summing over these two terms, where this is you have this U of G symmetry operator inserted, and their added was 1/2. So what we are missing is that if you do the modular transformation, you need to add two more terms. Namely that you need to term that introduce UG on the other cycle, and you introduce UG on both cycles. So you need these four terms. In order to make the partial function fully modular invariant. And existence of these two terms correspond to the second feature of gauging global symmetry, which is to add states that include twisted vector. What I mean is the following. So here we are talking about discrete symmetry, but you may be more familiar with gauging continuous symmetry, such as, for example, if the low energy theory has U1 symmetry. So if you gauge this U1 symmetry, you introduce photons. You introduce gauge fields that couple to this U1 symmetry. Introducing gauge field is the same as non-trivial connection of the fiber bundle, the vector bundle. So if you have taken undergraduate introductory course of quantum field theory and studied QED, or if you have taken some advanced course of electromagnetism, then you might have seen that in order to describe gauge theory, Maxwell theory, you introduce gauge field, and you can think of this gauge field as connection on the vector bundle, whose structure group is U1 symmetry. And if you non-trivial configuration of this gauge field correspond to considering non-trivial bundle structure, that you are considering some vector bundle which has non-trivial connection to it. In the case of discrete symmetry, there is no continuous field that you can have, but you can still have non-trivial bundle, because, for example, if your space is a circle, and if you have some discrete group action, it is possible to have non-trivial bundle over this space, because on each point you can have a fiber for which the field takes value. But then Z2 symmetry can act non-trivially on the fiber. And in particular, when you go around the space and come back to the same point and try to periodically identify the space, there might be the action of this discrete group. And this is what this is doing. Because what you have is that here I'm choosing this cycle to be the spatial cycle, and time propagation is in this direction. So what this is doing is that if you open this up, then you have a cylinder. You have a cylinder which is propagating in the time direction. And however, this operator that is implementing the symmetry operation is extended along the time direction, located at a point in the spatial section. So this operator is not doing projection, but rather when you go around the spatial direction, you come back not periodically, but periodically up to Z2 action. Okay, so this gives rise to the twisted set. Okay, so modular invariance automatically requires that you sum over this twisted sector. But this, you can also see that from the understanding precisely what we mean by gauging something. Okay, so with this understanding, the partial function for this circle compactification with Z2 symmetry, the orbifold, is given by the following formula. So these are the original two terms, but we have two more terms, and these are given by different powers. And then also there is an extra power of 2 to the q over 16 and q to the 1 over 24 and 1 minus q to the n over 1/2 square and twice of q over 16 q bar over 1 over 16. Okay. Okay, by modular invariance, we need to learn one more thing in addition to what we have seen. That is that if you try to gauge this discrete symmetry, we see that we need to introduce, or we need to restrict the Hilbert space to be group invariant, and also introduce twisted sector. But modular invariance also tells us the energy of the ground state energy of the twisted sector, and also the degeneracy. So you have factor 2 here, so that there's 1/2 here, but there are 2 of them. So that means that lowest energy state, there are 2 states in the twisted sector. And moreover, the ground state conformal dimension is 1/16. So therefore, Z2 twisted sector the ground state, there are 2 ground states with H and H bar is equal to 1 over 16 and 1 over 16. Okay, so this is what we can decipher from this construction. Okay, so this is very important, and this will be the basis of what we are going to do. So I guess in the remaining 10 minutes, I want to say one more thing, which is that we can easily generalize this for other objects. So far I just considered the case when target space is S1, but we can also consider this for more general space. And for example, one of the simplest interesting case is T4 over Z2. So what I do is that instead of 1-dimensional torus, we consider 4-dimensional torus. And so there are now 4 coordinates, and the Z2 acts by simultaneously flipping X. So this is an interesting example because this actually belongs to the family of 4-dimensional compact space satisfying Einstein equation called the K3 surface. Just like Narayan compactification, the K3 compactification comes with single connected modular space. And in fact, this simple geometry is in the family. So by understanding this compactification, it can give us some insight into this more general complicated family of compactification. So this is the first step in understanding. And K3 is actually the first non-trivial example of what's called Calabi-Yau manifold. Calabi-Yau manifold can be defined in any even dimension. And in 2 dimensions, it's just a torus. But in 4 dimensions, there are non-trivial Calabi-Yau manifold. And in compact case, they are all belonging to single family called K3. So this is actually first non-trivial example of Calabi-Yau manifold. And this belongs to that family. So this is actually the first interesting example. Okay, so let's study this in the remaining 10 minutes. And the first observation you make is that because we can just do the, so this is the same Z2 action. So we can do the same analysis. You consider G invariant sector and you introduce G twisted sector. So let's look at the Z2 twisted sector. Okay, so you can ask how many fixed points there are. Okay, so there's one important thing I forgot to say, that here I said that there are 2 ground states. Why we have 2 ground states in this case? The reason that you have 2 ground states in this D2 orbifold case is related to the fact that there are two fixed points in the Z2 action. So remember that we started out with a circle, which is S1, and but then Z2 action turns out into the line segment. Okay? And end point of the line segment was 0 and pi r. And the special thing about these endpoints was that these are the points that were invariant at the Z2 action. All other points are identified pairwisely like that. So there is something special about this endpoint. Okay, so these are called fixed points. Okay, and okay, and there are two fixed points here, and that is actually related to the fact that there are two ground states in the twisted sector. So namely, for each fixed point, so this is related to number of fixed points. Okay, so in the case of T4, there are actually 16 fixed points. And the reason you have 16 is that this can be regarded as a product of the full product of these kind of things. And although T2 acts diagonally, but in terms of counting the number of fixed points, you can say that how many fixed points are there for each of the four directions. And for each of the four directions, you have two choices. So therefore, you have 2 to the 4, which is 16. So you have 16 fixed points. And you have 16 fixed points. Each has conformal dimension 1 over 16 in each one of these directions. But the conformal weights add up because for each direction you have 1 over 16, but there are 4 of them. So therefore, H at H bar is equal to 4 over 16, 4 over 16, which is 1 quarter. 1 quarter. So for twisted sector, you have 14, 1 quarter, and 1 quarter conformal dimension, and there are 16. Okay. So that's interesting. So this is a bosonic string. But we can also make superstring. So let's suppose we consider type 2 A superstring. Okay, it turns out that it doesn't matter whether we consider type 2A or type 2B in this case, because as soon as you compactify on the circle, then type 2A and type 2B become equivalent. So you can just say type 2, but for definiteness, let's consider type 2A superstring. So then we also have to consider fermions. And fermion is also twisted for both left and right, because the worldsheet supersymmetry requires, since worldsheet supercharge is of this form. So in order for the Z2 action to preserve the supercharge, if you flip the sign of x, you have to flip the sign of psi. So therefore, you have to consider this. So that means that Z2 sector, Z2 twisted sector, include the spin field. Namely that the fermion is also twisted, so that means that you have to introduce spin field, which flips the sign of sigma. So remember when we talked about spinor fermions of the worldsheet, there is an operator which maps the fermion to NS sector to Raman sector, etc. And this is exactly what this does, because if you start with NS sector, if you go around the circle and come back, you get a periodic anti-periodic boundary condition. But if you combine that with this action, periodic boundary condition becomes anti-periodic boundary condition, etc. So as far as fermion concerned, Z2 sector, going to Z2 sector correspond is the same as going from NS to Ramon and Ramon to NS. Okay? So therefore you have a twisted sector, and so twisted sector has conformal dimension 1/16, and again there are 4 of them. So you get 1/4, 1/4. So that's where that's what fermion gives. So if you combine them, then the ground state of twisted sector as H and H bar is equal to 1/2. Okay? But remember that in the heterotic the type 2 string theory, this is the conformal dimension that needed to give rise to massless scalar field. So for each of these twisted sectors, it gives rise to massless scalar field. And if you have massless scalar field, it can develop expectation value, and so therefore it can describe the parameter of the theory. So namely that these are moduli. Because you can try to count the number of them. Well, originally you had the 16 as we counted as far as the number of twisted sector concerned. But there are also fermion boundary condition, and you have NS sector and the Ramon sector because of this kind of twisting, and it gives rise to additional 4. So in total you have 16 moduli. Okay, so are these the only massless scalar field? Well, there are more because you have T4 over Z2. And in T4, you can have a metric and antisymmetric tensor field. And you can count them. So basically, these are 4x4 matrices. And this is symmetric and this is unsymmetric. So therefore, the total number of independent components of G and B is equal to 4 times 4, which is 16. So if you add them, there are 80 moduli. Okay. Well, why is this interesting? So far we consider type 2. So what we show is that if you consider type 2A superstring on T4 over Z2, there are 18 moduli. Namely that the space of possible configuration of type 2 string on this geometry comes with 18 parameters. Now, this theory has 16 supercharges. Because originally type 2A theory has 32 supercharges, but Z2 action breaks half, so you have 16 supercharges. But if you can also consider heterotic string. On T4. Okay, so this is given by Narayan compactification that I mentioned earlier. So it is O 20, O 16,4 divided by O 16. And O4. And the dimension of this is also 80. And it also has 16 supercharges. out that low energy effective theory of type 2 string on this geometry and heterotic string on this geometry has exactly the same structure. So this was actually known some time ago, and it was regarded as miraculous, but it was demonstrated by the series of work by Witten and others in the mid-90s that this is actually not a coincidence, that there is actually a duality symmetry between them that connect to these seemingly different string sets. Okay? So I hope that we'll have a chance to discuss that in the next course. Okay, so that's all I wanted to say. I'm sorry that I ran over a couple of minutes, but I hope you can spend maybe half an hour to present your project. Okay, thank you very much. So I'm going to stop this one.